Hey everyone, my name is Jad Silbak. I'm going to talk to you about explicit uniquely decodable codes for space-bounded channels that achieve list decoding capacity. This is a joint work with Ronen Shilton. Okay, so let me start by describing our setup, and usually the story is told as follows. We have a message M that we wish to send through some or using some noisy channel. Now, because this channel is noisy, we're not going to use send M as is in the clear. We're going to first apply some encoding function on M that is going to add some redundancy into this original message. So hopefully now, after adding this redundancy, we get this code word Z and we send it through the channel. The channel, as I said before, might induce some errors. But as I said, because of this redundancy, hopefully the other party can now apply some decoding function on this damaged code word and be able to recover the original message. Okay? So we said that the encoding and decoding recover against the channel C if for every message M, the decoding of this damaged code word is still able to produce the original message M. Okay? Now, the rate of the code is the ratio between the length of the message and the length of the encoding of the message. So we want this to be as large as possible because this means that we didn't add a lot of redundancy. So there are two questions to ask yourself whenever you consider a channel or a family of channels. So first is, what is the capacity of this channel? So whenever you think of an adversary here that induces errors, or a family that is chosen adversarially, you might ask yourself, what is the best possible capacity against this channel, right? And by capacity here, we mean, what is the optimal rate achievable? Okay. And the second question is, can we have efficient encoding and decoding? And for us, efficient will mean polytime. So we mean, we ask ourselves, do we have polynomial time encoding and decoding algorithms that are good against this class of channels? But you might ask yourself for something even more restrictive, like linear time and etc. Okay. So these are perhaps the most important questions. And let's now consider, or let's examine what we have in what we know in the literature. Okay. So there are two main extremes in the literature when we consider channels. So the first one is the Hamming channels. And here, by Hamming, I mean the channels that can induce or change any P in locations in the encoding. So these are channels that are all powerful in a sense that they can change any P in positions they want, and they're tailor-made to do the most harm to this specific encoding that they see. So the channel is an adversary that fully depends on the code word itself. Okay, and this gives rise actually to a notion of distance, because otherwise you can't guarantee this recoverability. But weirdly enough, even though this is the most studied class of functions, or let's say channel out there, the optimal rate is still unknown. So we know that it is impossible to have a rate greater than 1 minus entropy of P. In fact, it's strictly smaller than 1 minus entropy of P. And here, I mean entropy of P here, the entropy is the Shannon entropy function. So for every P in this range, we know that the ham of P, which is the adversary that can change any P in positions, has rate which is smaller than 1 minus entropy of P. Okay, and whenever P is larger than 1/4, then we know that the rate is 0 because no such code exists. Okay. But on the other hand, we know that codes that achieve rate 1 minus entropy of 2P exist. This is the well-known result by Gilbert Vershamov that showed that using a probabilistic argument that there exist codes that in fact achieve this rate up to some, let's say, small epsilon. Now, the problem with this is that we don't know any efficient constructions for the majority of the P's. In fact, only recent results that show that that are able to show that there exist efficient constructions that achieve this rate are quite recent, and they only apply for a small range of P. Okay, but still we don't really know where the correct capacity lies. It's somewhere between 1 minus entropy of P and 1 minus entropy of 2P. Okay, but at the other end, we have another extreme, which is what we usually refer to as binary symmetric channels or Shannon channels. So these are channels that will flip every bit with probability P, and they don't even look at the encoding itself. They're independent from the encoding, they're independent from encoding of M, and they're not a function of M. Okay, so the channel doesn't even look at M, and it can choose its errors independently. And whenever it sees 0, it says, okay, with probability 1 minus p, I'm going to stay the same, and with probability p, I'm going to flip. Okay, and it does so for every bit. But unlike the Hamming channels, which, as I said before, we don't have really efficient constructions that achieve the optimal rate. In fact, we don't really even know the optimal rate. So for Shannon channels, we know that the optimal rate is 1 minus entropy of p. And in fact, we do have efficient constructions that achieve this rate and give us, let's say, even linear encoding and decoding. So we have now two extremes. At the one end, we have Hamming channels that are all powerful in a sense. They're not bounded in any way except the amount of error they can induce. On the other hand, we have these kind of channels that don't even look at the encoding itself. They just apply some random noise, right? And it's actually natural. It's a natural question to ask if we can actually have something in the middle that might benefit from the efficiency of efficient constructions of binary symmetric channels, but is still able to deal with adversaries that aren't so stupid, right? Are more intelligent in a sense, that might consider even be a function of the encoding itself, okay? And this gives rise to an intermediate concept of channels, something that lies between the Hamming case and the Shannon case. And it's important to note here that this channel can't be all-powerful, because if it was all-powerful, then we're simply reducing to the Hamming setup, right? So this channel needs to be drawn from some bounded, let's say computationally bounded class of functions. And in fact, Lipton himself already suggested such families or such channels that, first of all, can induce some bounded amount of error, let's say fraction p of errors, p(n) errors. And second of which is that they're drawn from some bounded computational class. So for example, think about space-bounded, time-bounded, and etc. Okay? In this work, we're going to consider codes that can recover or are good against small online space channels that can induce at most p errors. So we're still in this framework where the channel can induce at most, let's say, fraction p errors, and is the adversary that actually is now responsible for inducing this error isn't all powerful, but is drawn from this, let's say, online space channel. Okay, so let's be a bit more specific about what we mean by online space channels. So for a parameter s and a parameter p, we define the class of function space sp to be the following. So these are functions that are bounded by the amount of error they can induce, and they can induce at most p errors. And they must be implemented in one pass using only space S. So think about the following. It's a procedure that reads the input in one pass. It goes over the input, and whenever it reaches an input I, it needs to decide whether to flip this bit or not, okay? Now, this procedure can be seen as following, which is a function that has some internal state Q composed of S bits. And whenever it reads the ith bit, let's say, it updates its internal bit and decides whether to flip or not. So there are two things to note here. First is that C has to decide whether to flip the ith bit even before seeing the rest of the code. So in a sense, it's committed to the error it induces even before knowing what comes after. And the second point is that when making decisions, C remembers only S bits of information of what transpired before it. So if it wants to induce an error here, it doesn't remember everything that came before. It only remembers, say, S bits of information of what happened. Okay? So we now have this weaker notion or weaker class of functions that we can consider. And hopefully, maybe for this class of functions, we're now able to have efficient encoding and decoding that achieves good rates. But we still have a problem, because it turns out that even if you have a code that is good against space 0 with non-uniform advice channels, then it's also good against Hamming channels. So we're not doing any relaxation here. This is still the same problem. And this is because if you have two, let's say, code words that are close to each other, then using some non-uniform advice, you are able to push this encoding into the radius of the other code word, and then the decoder will fail. It won't be able to know where it came from. Okay, so we're still not not able to make any progress, but there's still a solution for this, at least according to Guruswamy and Smith, and this solution is stochastic codes. So what are stochastic codes? These are codes that have encoding that is randomized, and the decoding that succeeds only with high probability. So we have these two relaxations, and these relaxations, I'm going to explain them in a bit, help us even circumvent this problem where the channel is some bounded channel, the channel is drawn from this bounded class, but may have some non-uniform advice, okay? And for crypto people out there, this is similar to what we refer to as non-malleable codes, okay? So let me now tell the story again, this time from the point of view of stochastic codes. Okay, so what are stochastic codes? Again, we have a message M that we wish to send through some channel, but unlike before, we're not gonna send M just the encoding of M, we're gonna encode M using some randomness R. So R is used as a uniform Gaussian randomness, and it's being used in the encoding of M. And we get a code word Z that we're gonna send through the channel. As I said before, the channel induces some errors, and in our case, it's gonna be sampled from, or gonna be chosen from an online space channel. Now, the decoder takes this damaged code word and needs to recover the original message. And let me note here and emphasize that C, the channel, and the decoder don't receive this randomness. So this is, in a sense, a very lightweight setup. We're not proposing any uniform randomness that is being shared by the parties, nothing of the sort. This is a very lightweight setup, and this is what this is the right definition if you don't want to make any assumptions. Let me also emphasize that the rate also remains to be the ratio between the message and the encoding of the message. So even though I'm using here randomness in the encoding of the message M, it doesn't take any part in the computation of the rate. So it's not real information that I'm sending, so I don't expect it to be part of the message, okay? So here's a formal definition. Let me go over it slowly. So an encoding function that takes two parameters, a message and the randomness, outputs an n-bit code word, and is said to be stochastic for a class of function, let's say small space, if there exists a decoder that for every message M, this is crucial, for every message M and every adversary from this class, the decoder that actually now gets as an input a damaged code word by this channel C is able to recover the original message with overwhelming probability. In our case, it will be 1 minus some negligible function, okay? And we say that the code is explicit if the encoding and decoding are polynomial, that is, they run in polytime. Okay, so using this notion of codes, let's now try to state our result. And our result has two aspects. So the first result and our main result is the existence of explicit, and here again by explicit we mean with efficient encoding and decoding algorithms. So we have an explicit binary uniquely decodable stochastic code for online space for S that equals n to the power of some delta, where delta is a constant greater than 0 and less than 1. Now this code will have a rate that equals 1 minus entropy of P. And let me say here that this is optimal, right? This is the best you can ever hope to get. And in fact, we are able to achieve this for very large space, okay? And our other result is characterization of space, or for a characterization of the capacity of space for for space that even is larger than this, for S that goes to n to the power of 1 minus little of 1, we know that the capacity, or what you can ever hope to achieve, is 1 minus entropy of P. And whenever P is larger than 1/4, then this means that the capacity is 0. So we have a full characterization of the capacity for space-bounded channels, even for larger space. Okay, so the first result is an explicitness of the construction that can be used, and the second one is the characterization for space, even for larger space. Okay, now note here that this is very weird because in a sense this means that the rate isn't continuous at P equals 1/4, right? And this is not usually how it happens. Usually this is not the case. Yeah, so it's like it goes all the way until P minus 1/4, and then whenever P is larger than 1/4, it like instantly becomes 0. So in a sense, we have something that enjoys the benefits of binary symmetric channel for something that is even stronger, right? We have a much stronger class now, but we're still able to have an explicit construction that achieves optimal rate. And in fact, this is the same rate for binary symmetric channels and also for list decoding channels, okay? Okay, and the other thing is that, and this was said by Goswami and Smith in their original paper, is that essentially all non-adversarial channels studied in information theory, like burst channels and the binary symmetric channels and etc., are all can all be implemented in small space, even for space that is very small, even logarithmic. So what we have here is a unifying framework that actually is able to deal with all of these channels, and even much more for a much larger space. Our space is, of course, greater than any polylog. Okay, good. So let's now talk about, or let's compare our result to previous results and see where we stand. Okay. So there are two lines of work that are related to ours, and the first is that deals with list decoding for space-bounded channels. So this was started by Goswami and Smith, and later continued by Sheltel and Silbach, and Kuparti, Sheltel, and Silbach. And they showed that there exists explicit construction for list decoding. And by list decoding here, we mean that the same procedure as before for stochastic codes, but this time, instead of outputting a single message, the decoder will output a list of constant size, such that at least one of them is the original message you started with. Okay? And let me point out here that unique decoding is usually much harder to achieve than list decoding. And to the best of our knowledge, no prior explicit constructions are known for bounded classes of functions that is able to achieve unique decoding. And another thing to point out here is that for the Hamming channels, the capacity for unique decoding is smaller than the list decoding. So actually, we don't know what the capacity for unique decoding is, but we know that it's much smaller than the capacity for list decoding, which equals 1 minus entropy proof. Okay. So the other line of work to consider is the line of work that is interested in space-bounded channels where space is equal to n. So in a sense, we're only interested in online channels. Okay, so we have an online channel that goes over the input in one pass, and it remembers everything that came before it. It's not bounded in space. S here is essentially n, everything. And you can remember everything, and you need now to decide what to do on the ith bit, considering what you saw so far. Okay? So in this line of work, the aim was not to create explicit constructions, but only to characterize the optimal rate. And to the best of our knowledge, no prior or no explicit constructions are known for these channels. We know that there exists a constant p, such that a channel, or a casual channel, that is to say, a channel that reads the input in one pass and can answer, let's say, p infraction of errors, has a rate that is strictly smaller than 1 minus entropy of p. And as we said before, this is the rate for space-bounded channels. So our result gives a separation for space channels or space-bounded channels and casual channels, which are not bounded. Okay. So for the rest of this talk, let me try to give you an overview of our technique and our strategies for proving our result. And our starting point is going to be codes that achieve list decoding for space-bounded channels. So we're going to use the result by Kuparti, Sheltel, and Silbach that gave us list decodable stochastic codes with optimal rate, 1 minus entropy of p, for the same space, only the algorithm will output a list of size L. Okay, so here we have an algorithm that will output a list and not a single candidate as we want. And our method is going to be very straightforward, perhaps the first idea you may think of. And it is to try to identify the correct message in this list. Okay. Now, while this is quite naive and straightforward, I want to point out that this rarely works in real life. And for example, for the Hamming channels, this of course can't work. Okay, so while this approach may be natural, this is usually not useful. And our strategy is going to be as follows. We're going to try to recover the algorithm. We're going to use a recovery algorithm, that will produce L possible candidates. And each of these candidates is going to be sent to the decoder. So I'm not going to explain this formally, but think about it as follows. We have some recovery procedure that will give us some candidates, such that at least one of them is an encoding of the original message. And for now, I don't know anything about the other candidates. Okay. So this is going to be an encoding of our original message, and we're going to use a code that is good for binary symmetric channels. And the reason that this is good is because we can actually make sure that all of these false candidates are going to be hit by a space-bounded channel. So the error that is being induced for them is going to be from some space-bounded channels, except for the original message, which is going to be hit only by binary symmetric channels. So if our encoding here is good for binary symmetric channels, then this means that we can actually hope to recover the original message. And what we do here is we can now decode all of these candidates. And as you see here, when we decode all of these candidates, because if we are now able to decode for binary symmetric channels, then we can actually recover the original message, even though for now we don't have any control over all of these candidates. So this is how you get list decoding. But what we do here is we try to do the following. We try to arrange for all of these false candidates to be pseudo-random against the channel. Okay, so this channel C that is going to take these like strings that for now I don't have any control over, we're going to make it so that all of them appear to be pseudo-random, and this takes a lot of work. I'm not going to go over the details, but even let's pretend that they're not even pseudo-random, they're fully random. Okay, so what we get here is we have L random strings, and for each of them, the channel is going to apply noise. So for each of them, C is going to be applied on Z1 and ZL, so that we're going to be hit by noise induced by some space-bounded channel. And finally, what we have here is that with the exception of the correct message, which is a decoding for binary symmetric channel, and which is encoded by M, all other candidates are a decoding for some noisy code word that, are a decoding for a random string hit by some noise induced by some space-bounded channel. Okay, and the good thing is that we are able to infuse our codes with evasive properties. And by evasive, we mean that with high probability, the binary symmetric channel, or sorry, binary symmetric decoder aborts if it receives a random string that is corrupted by a bounded channel C. So in a sense, all of these candidates are going to be aborted. We're able to identify when this happens. So our decoding algorithm is constructed in such a way that it knows whenever it receives a message that was hit by whenever it receives a message that is random and was applied with noise that was induced by space-bounded channel. Okay, with the exception of the original message, because this can actually deal with the random error, with binary symmetric errors, then we are able to recover the original message. And this means that we are able to trim down all the false candidates. We're going to stay with the correct one. Okay, so this is very high level overview of our construction. There are many details that I'm going over. I'm not even attempting to go into it with the time I have, but I want to point out that this evasiveness property is quite interesting, and we think that it might find application in other areas. Okay. So let me go say this once again. So we want this property that when a decoder receives a code word that is the product of a random string being induced with errors applied by some space-bounded channel, then this decoder is going to abort. Okay, and if we have this property, we are able to have uniquely decodable codes. Now, there are many other areas I'm going over and many technical details and hurdles that you need to overcome in order to achieve this result, but this is one of the key ideas we use in our construction. Okay. So now let me conclude our result and state our open problems. And let's conclude by restating our main result. And our main result is an explicit binary uniquely decodable stochastic codes for online space, for space that is n to the power of some of theta of 1 with rate equal to 1 minus entropy of p. So we have an explicit uniquely decodable construction that achieves optimal rate 1 minus entropy of p, and recall that this is strictly larger than what is achievable for the Hamming case. So we have a separation here. And the second thing is that I want to point out as this evasive codes property, which says intuitively at least that channel can't push the decoder to correct a random string without it noticing. So if you have a random string and then a channel is trying to like push you into decoding a or to deceive you into thinking that you're close to some vicinity of a real code word or some valid code word, then a channel can do that. Okay, and this property appears to be useful, at least for us. Now, open questions are or can be set it as follows. For example, can we have unique decoding for other classes of functions, perhaps AC0, perhaps size channels, and etc. And perhaps can we find other applications for evasive codes, which we think are quite interesting and may be useful for other applications. Okay, so that's it. Thank you all for listening, and see you all in the talks.